problem is actually an exercise in inertia and an exercise in looking at the importance of inertia. So let's start with the standard modified Atwood machine problem. And we are going to look at probably only about 3 different problems before we run out of time. And this is our basic modified Atwood machine. We'll start with a coefficient of kinetic friction of 0 between the block and the table. And for the time being, this semester, all of our pulleys are going to be massless and have no friction. When we deal with rotational dynamics next semester, we'll add mass back to the pulleys. So a modified Atwood machine is generally a problem in which there is an external force provided by gravity that causes a system of objects to be moved. In this case, I don't think there's much of a surprise. M1 and M2 are both going to accelerate due to the unbalanced force acting on M2. Does that seem pretty reasonable? M2 is experiencing how many forces? Thank you. So 2 forces. I expect that you guys would have no difficulty recognizing that downwards, there'll be weight. But what you do next, I will be critical about on your next test. There being no friction on the surface of the table suggests immediately that there will be a tension upwards, but that tension will not be as big as the weight of the object. The only way M2 can accelerate is if there's an unbalanced force acting on it. And although many of you won't write that down, you novices had better. Understand the only way it accelerates is if there's an unbalanced force acting on it. There's so many easy ways to trick you about this. And I will attempt all of them on your next test. And then you'll cry foul about why you do so bad on a multiple choice. And I'll say, I told you I was going to do this. You didn't listen. So I'll say it again. The only way something accelerates is if the net force is unbalanced. I think we all agree the system's going to accelerate downwards and to the right. The only way that can happen is if tension is less than weight. Your picture should definitely show me that. At the same time, the box and the table is going to experience tension to the right. It's critical at this point that we recognize that all the pulley does is redirect the force. Because the pulley is massless, it doesn't take an unbalanced force to turn it. So the tension in this string is going to be the same everywhere. So due to Newton's third law, the tension on M1 has to be equal and opposite to the tension on M2. Thus, those 2 arrows should be drawn the same size. That also doesn't talk much, but belies the idea that there are still 2 other forces acting on M1, but they're really not going to contribute to this problem. They would contribute if the surface of my table was at an angle. They'd contribute. They would contribute if there was friction on the table, but for right now, they don't contribute. These are the forces that act on the objects in my system. My expectation is that I can pause right now and you guys could come up with an expression for the acceleration of the system. Before you do this, though, if you've done this before, you probably know how to handle what I'm about to talk about, but I haven't been your physics teacher last year for all of you, so I don't know really what you were taught on what to do next, because textbooks do this different than I do this. Textbooks would have you apply a standard coordinate grid to everything in your system, applying positive and negative based on your coordinate grid. I don't do that. That doesn't make a lot of sense to me. What I like to do instead is to provide consistency. I like to establish a consistent direction for positive by identifying the object that's likely to turn and saying that all things connected to this object will be moving in a positive direction based on the direction of my arrow. This is an arbitrary decision, but one that should be made early in your problem. By making this decision, I am saying that anything that points to the right on this object is in the positive direction, and anything that points downwards on this object is in the positive direction. And this is the part that's important. I am intentionally deciding the positive direction for acceleration. That's an intentional decision. So even if I don't know what the actual direction of the acceleration is, I am making an intentional direction here. If you do it the way the book does it, you will find that you have to keep track of more negative signs than if you do it the way I'm doing it. So I will encourage this way. If you don't like my way, then do the book's way. They're both right. In fact, the book is probably more right than this. Either way, you take a moment and come up with a expression for the acceleration. You guys are sharp. This is mechanics. And I don't think I have to baby step every little thing. So you've got 60 seconds. All right, so you should be done by now. This is pretty straightforward algebra, but that doesn't mean that it's straightforward to you. I'm hoping that you recognize net force equals ma. This is a second law problem. I said it's going to accelerate. So we should have tension equals m1a on this side. And you should have m2g minus tension equals m2a on this side. Substitution, right? Now, if you substitute, you should get an expression for your acceleration. It's pretty straightforward. I'm going to encourage that you look at something else here. If you are using my method for this, which means identifying a consistent direction for the acceleration, then when you do this, you can stack these up. It will automatically cancel out internal forces immediately when you add these two things together. So if you're looking for a way to save yourself time, and when there's 3 or 4 objects all being connected together, finding a way to save time might be in your future. It also proves something to you, I hope, that we were recreating Newton's second law for the system of objects. If you've done this correctly, what you should always have is the sum of all of the masses should show up some point in your problem. This represents the inertia of the system. In the future, it's going to be all the masses as they exist for inertia. Rotational inertia is a little different than linear inertia, but they'll still show up. So if you've done your problem right, at some moment, you're going to have a list of all the objects times the acceleration. They represent the inertia of the system. The left side will represent the unbalanced forces acting on the system. Things that are unbalanced tend to be friction or gravity or something like that acting on your system. That's how you can kind of tell if you're right. Substitution will work, and I'm not saying don't use substitution. I'm saying that if you use my method here and point the consistent direction for positive, you should easily see things that are going to cancel out between these sets. Generally, it's easier to eliminate internal forces and solve for the acceleration first than it is to eliminate acceleration and solve for an internal force second. So I would encourage you to find the acceleration first. In this system, the acceleration is the unbalanced force divided by the inertia of the system. Not terrible, but that's what we should see. Now, if you want the tension, you should plug it back in. That part's not too hard. I would probably plug it in here. I think that's probably a better place to plug it back in to find the tension than plugging it in the one above. Wouldn't you guys agree? So I just have to multiply by M1 to get the tension. So tension is, and this bears at least a moment's recognition. For you mathy folks out there, you know, the mathletes among you, this is a form of weighted average. So it's not unusual to see this kind of weighted average. The bigger mass, in this case, takes the lion's share of the answer. And that's appropriate, as it would tend to determine how the system would behave. Notice making either mass bigger increases the overall tension. That doesn't surprise me very much. I hope it doesn't surprise you. All right. Modified Atwood is not particularly interesting, but I need to at least show you something. So I'll put that away for a minute and consider this modified Atwood machine. This has been on, I don't know, a dozen tests, and it successfully gets students to choose the wrong answer. That's why I like it. That's So I want to make a test to watch you guys squirm and get mad when we go over the multiple choice. This is the one to use. And I can't tell you the number of tests it's been on, but it's been a lot. So in this test question, there's a modified Atwood machine. So on one of them, there's a all right, so back to where we were, I hope. In some of these, they have like a 10 kilogram box here, 10 kilogram box here, and they'll put a 5 kilogram box here, or say that they are pulling downwards with 50 newtons of force. A 5 kilogram box weighs 50 newtons. And I'll ask, in which system is the acceleration the greatest? And a lot of people will indicate right away that they're the same. And I'm not going to call you out on who thinks these are the same, but it's going to be substantial. And in multiple choice, it's easy to manipulate those answers to make them sound like they're the right answer. But the right system accelerates less than the left system. Has to. The right system has a 50 Newton force acting on 15 kilograms of inertia. But the left system has 50 newtons of force acting on 10 kilograms of inertia. So even though both of them have the same unbalanced force, this system accelerates slower. More inertia in the system. Atwood machine questions are all about trying to exaggerate inertia, and this is an excellent way to do so. On the left side, there's 50 newtons of tension in the string. If I ask you how much tension is on the right side, a bunch of you will say 50 newtons of tension on the right side, but it can't be. It has to be less than 50 newtons. But I'm setting you up for failure because of the left side of the problem, and you will be distracted. Even now, some of you are making that face, but the right side, if it accelerates, the only way it can accelerate is if there's less tension than 50 newtons. The box weighs 50 newtons. For it to accelerate downwards, the upward force of tension must be less than 50. Again, though, put both these pictures side by side, start asking multiple choice questions, when you got a minute and 15 seconds to decide, you will be fooled because you won't think it through. Always prioritize inertia over force. Consider inertia first, and then consider the unbalanced force. Don't think it reverts the other way. In both of these cases, there's the same unbalanced force of 50 newtons. So, again, I don't think they're hard, but I think you are easily fooled. Now, I'm going to move on a little bit. So here we go. We have a standard Atwood machine question. I have a frictionless massless pulley. So for all of these, we're talking frictionless and massless pulleys. But I have two masses being hung on it, M1 and M2. I think I don't need to say much more to ask you politely to come up with an expression for the acceleration of this system. You guys are smart. I don't think I have to do every little thing. So let's give 60 seconds for the acceleration of this system. And if you haven't identified a consistent direction for positive yet, that should have been your first thing. Have you drawn an arrow over the top of the pulley to indicate what you're going to call positive? Because if you haven't, you've already forgotten the things I've told you in your notes. So for the whole class, does it matter? Does one of these look bigger than the other? This is an arbitrary choice. You need to pick a direction and be consistent. So for the whole class, let's choose this direction to be our consistent positive direction. And I hope it's the opposite direction that all of you chose, so you have to do some work over again. Go. Now, that's as much time as I would hope it would take you to get most of the way done with this. I know clearly by watching you guys that might not be true. But before we get any deeper into it, did you take care to make your free body diagram appropriate? The tensions should be the same upwards. Newton's third law requires the tension be the same value. Therefore, the upwards arrow should be the same size on both objects. However, the only way the object on the right accelerates downwards is if the arrow representing weight is bigger than the tension. And the only way the box on the left accelerates upwards is if the tension is greater than the weight. And since the two tensions have to be the same size, then, well, you should be having a diagram that looks like my diagram. It is not unusual on the AP exam for them to have markers on the free body diagram section to ensure that your tensions work out to show that they are exactly the same and that your weights differ in order to demonstrate an unbalanced force. I know you're not always thinking that way, which is why I'm stopping to make sure that you are. Again, everything on the board behind me is still what we're doing. So T minus M1G equals M1A, and M2G minus T equals M2A. That okay? Any question about that? So again, substitution, but I would encourage you to consider just stacking them and adding them. That's going to produce the right side will be M1 plus M2A. Some of the masses shows up. T's are going to cancel. And we get M2 minus M1 times G. That gives us an acceleration that looks like this. M2 minus M1 over M1 plus M2 times G. This is an easy way to measure G, an Atwood machine. Measure a couple of masses, figure out the acceleration by using a motion sensor. You can use that to figure out G pretty easy. It's a straightforward lab. They asked this on an exam 2 years ago. How would you structure your lab in order to measure G using an Atwood machine? I think I see a way to do so. Do you see a way to do so? So I'm hoping. We'll talk about linearization. We're going to do this lab in a week or so. It would have been the lab we would have done yesterday, but we're just a little behind. So we'll do it next week. Negative signs. Did that call your attention to what the negative sign could mean? I hope so. Obviously, that allows for a negative answer, a positive answer, and a zero. So I don't think it's a surprise if the two masses are the same. It doesn't accelerate. And that's what gives you the zero. Also, you could have chosen the wrong direction for positive. That's fine. It says it right there. If M1 is greater than M2, it would have accelerated the other way. Good. We now know the conditions to which that exists. You should always pay attention to those negative signs. Now, I'm going to ask you to do a task that I don't really want to do in class because it takes too long. And it's algebra, and it's deep. But you should figure out an expression for the tension. And I'm going to tell you the answer, but I'm not going to perform it because there's other things we should talk about today that I think bear better use of our time, since this is a physics class, not an algebra class. But you should do this because it is an excellent practice for what I would say is crappy algebra. And some of you, your algebra skills leave little to be desired. Oh, wait, there's no 2 in the bottom, just 2 in the top. There. That is the expression for the tension in the string. And you can only get this one way by taking the acceleration and substituting it into either to the top equation or the bottom equation. Pick one or the other and then solve for t. You'll get this. And there's no surprises here. And the way you can test to make sure there's no surprises is if M1 equals M2, this comes out to be 2m squared divided by 2m times g. Right? If M1 equals M2, they are the same value. The 2's cancel, one of the m's cancel, and we find that the tension equals the weight of one of the boxes. Well, that'll prevent an acceleration. That has to be right. But trust me when I say it's a feat of algebra to get this. You should do it. You should try it. And I would expect that, if you have difficulty, you'll ask. That's all I really want to say on the Atwood machine question here. Do you guys have any questions about this one? So now let's talk about what I think. I'll say something for all the staff. Nobody ever makes it this far into the videos. I don't even know why I'm bothering. But I'll say that. Oops, forgot to record all that. So if you're doing the friction one, there's the answer. And you should go back and plug it in and show that the tension is greater if it's slowing down. 15 seconds. That's good. Time to adjust them all. But there's like this one cracks me up because people get all weirded out about it, but I don't know why. There's, oops, not that. Put a box here and perhaps a extension on the table here. So it's not a box, that's just a piece of the table. And have the string go here and here. If the box has mass M, and I tell you the system is attached to the table, can we all agree the tension in the string has to be mg? Seems not unreasonable. All right, so then I take the box away, put another pulley over here, like so. I don't mean for this pulley to be bigger, so they're smaller. There we go. Hang a box over here. And let's say I hang the same box over here. Same mass. So now I'm hanging two boxes. What's the tension of the string now? Still just mg, right? It's not twice the mass of the boxes. Some people think it is because you're hanging two boxes. But how is it different to this mass? Net force has to be 0. The tension still has to be the same. It has to be the weight. Has to be. You might want the tension to be more because you're hanging two boxes, but it's not. The tension's still the same. The table held onto the string to provide enough tension so that the box wouldn't fall. Now the other box is holding onto the string with enough tension to prevent the other box from falling. Same thing. And you guys can imagine me taking this entire system and just putting the whole thing on a ramp. I sure will. If I'm going to write a test, it's going to be one of those. Why? Because then I can test a inclined plane problem and a one of these at the same time. So unfortunately, that's the end of our time.